Hello there, and welcome. Tonight we're embarking on a journey through one of the universe's most fundamental constants, the speed of light. This isn't just a number in a physics textbook, it's the cosmic speed limit that shapes everything from the smallest particles to the largest galaxies. As we drift through these illuminating discoveries, you'll find that light carries secrets far stranger and more beautiful than you might imagine. The speed of light touches every corner of existence. It determines how we see the stars, how atoms hold together, and even how time itself flows. Tonight we'll explore how this seemingly simple concept reveals the deepest mysteries of space and time. Some of what we discover will feel gentle, like understanding why sunlight takes 8 minutes to reach Earth. Others will be mind-bending, like learning that nothing with mass can ever reach this ultimate speed. Each insight will open a window into the elegant physics that governs our universe. You might find yourself drifting towards sleep as these ideas flow quietly through your mind, or simply letting these cosmic truths wash gently over you. If you enjoy these nighttime explorations of science, feel free to like and subscribe below and share your thoughts in the comments. But for now, all you need to do is settle in comfortably, let your breathing slow, and allow the wonder of light's journey to carry you into peaceful rest. Let's begin. Light travels at exactly 299,792,458 meters per second in a vacuum. This isn't an approximation or an estimate. It's a precise definition that forms the foundation of modern physics. Scientists have measured this speed with such accuracy that we now use it to define the meter itself. 1 meter is the distance light travels in exactly 1,299,792,458 thousandths of a second. This remarkable precision came through centuries of increasingly sophisticated experiments, each one bringing us closer to understanding light's true nature. What makes this speed so special isn't just its constancy, but its universality. Whether light comes from a candle flame or a distant star, whether it's red or blue, visible or invisible, it always travels at the same fundamental speed through empty space. This consistency is one of the most tested principles in all of science, verified in laboratories and astronomical observations countless times. The journey to measure light speed began with simple observations. Early scientists noticed that lightning and thunder didn't arrive at the same time, suggesting that light traveled faster than sound. But measuring light's actual speed proved far more challenging than anyone initially imagined. The breakthrough came through increasingly clever experiments that pushed the boundaries of what was technically possible. Light from the sun takes 8 minutes and 20 seconds to reach Earth. This means that when you step outside and feel sunlight on your face, you're experiencing light that left the sun's surface over 8 minutes ago. In a very real sense, you're touching the past. If the sun were to suddenly vanish, Earth would continue in its orbit for those 8 minutes, bathed in light from a star that no longer existed. This delay isn't just a curiosity, it has practical implications for space exploration and astronomy. When we observe other stars and galaxies, we're always looking into the past. The nearest star system, Alpha Centauri, appears as it was over 4 years ago. The Andromeda Galaxy shows itself as it existed 2.5 million years in the past. Astronomy is fundamentally the study of history, written in light that has traveled across impossible distances. This time delay also means that our solar system exists in a bubble of 8-minute-old information. Everything we see of the sun, from its surface features to its solar flares, reflects conditions that existed when that light began its journey. In space, the present moment is always somewhere else, traveling toward us at light's eternal pace. Nothing with mass can travel at the speed of light. This isn't a limitation of our technology or engineering. It's a fundamental law of nature. As objects with mass approach light speed, something remarkable and counterintuitive happens. Their energy requirements grow without limit. To actually reach light speed would require infinite energy, which is impossible. This cosmic speed limit isn't arbitrary. It emerges from the deep structure of space-time itself. Albert Einstein discovered that mass and energy are related through his famous equation, and this relationship creates an absolute barrier. Only massless particles like photons can travel at light speed. Everything else, no matter how small or how much energy we give it, will always fall short. This limitation has profound implications for space travel and our dreams of exploring distant worlds. Even with perfect technology, journeys to other star systems would take years or decades at minimum. The universe enforces a kind of cosmic patience, ensuring that certain distances can never be crossed quickly, no matter how advanced our civilization becomes. Light behaves as both a wave and a particle simultaneously. This dual nature puzzled scientists for centuries and led to some of the most revolutionary discoveries in physics. Sometimes light acts like a wave, spreading out and interfering with itself to create patterns of brightness and darkness. Other times it behaves like a stream of particles, each photon carrying a discrete packet of energy. This duality isn't just a mathematical abstraction. It has real consequences that we observe in everyday phenomena. The colors we see are determined by light's wave-like properties, while the way solar panels convert sunlight to electricity depends on its particle nature. Both descriptions are correct, and both are necessary to fully understand light's behavior. The resolution to this apparent contradiction came with quantum mechanics, which revealed that our everyday notions of waves and particles break down at the smallest scales. Light is neither wave nor particle in the classical sense. It's something more fundamental, a quantum field that can manifest different aspects depending on how we observe it. Light can be trapped and slowed down dramatically in certain materials. While light always travels at its maximum speed in a vacuum, it slows considerably when passing through matter. In water, light moves at about 3/4 of its vacuum speed. In diamond, it slows to less than half. But scientists have discovered ways to slow light to truly extraordinary degrees. In specially prepared materials called Bose-Einstein condensates, researchers have slowed light to just a few meters per second, slower than a bicycle. They've even managed to bring light to a complete stop, trapping it within the material before releasing it to continue on its way. These achievements aren't just laboratory curiosities. They point toward future technologies for storing and manipulating information at the quantum level. The ability to control light speed opens possibilities we're only beginning to explore. Imagine computers that store information in frozen light, or communication systems that can pause and replay messages made of pure photons. These experiments reveal that even something as fundamental as the speed of light can be tamed under the right conditions. The speed of light connects space and time in ways that defy common sense. Einstein's theory of relativity revealed that these aren't separate entities, but aspects of a single fabric called space-time. The speed of light serves as a kind of conversion factor between space and time, showing how measurements of each depend on motion and gravity. This connection leads to some of the strangest phenomena in physics. Time dilation means that time passes differently for observers moving at different speeds. A traveler approaching light speed would experience time more slowly relative to someone at rest. What feels like minutes to the traveler could be hours or days to the stationary observer. Similarly, distances contract for objects moving at high speeds. A spacecraft traveling at nearly light speed would appear shortened to outside observers, while the crew inside would measure normal dimensions. These effects aren't illusions or measurement errors. They're fundamental features of how space-time operates when speeds approach that ultimate cosmic limit. Light carries information about the universe's history written in its wavelengths. As light travels through space, its wavelengths can be stretched or compressed by the expansion of the universe itself. This creates a phenomenon called redshift, where light from distant galaxies appears redder than when it was originally emitted. By studying these wavelength shifts, astronomers can determine how fast distant objects are moving away from us and how far away they are. This technique revealed one of the most important discoveries in cosmology. The universe is expanding. The farther away a galaxy is, the faster it's receding from us, as if space itself is stretching. The cosmic microwave background radiation provides even deeper insights into the universe's past. This ancient light, released when the universe was only 380,000 years old, carries information about conditions in the early cosmos. By analyzing its subtle patterns and temperature variations, we can map the seeds that eventually grew into galaxies and stars. Quantum mechanics reveals that light comes in discrete packets called photons. This discovery revolutionized our understanding of energy and matter. Rather than being a continuous wave, light energy is quantized, meaning it comes in specific, indivisible amounts. Each photon carries exactly the right amount of energy for its particular wavelength. This quantization explains many phenomena that puzzled earlier scientists. When light hits a metal surface and knocks out electrons, the process depends not on the light's intensity, but on the energy of individual photons. Bright red light with its lower energy photons can't eject electrons even at high intensities. Dim blue light with higher energy photons can trigger the effect immediately. The photon concept bridged the gap between classical physics and the quantum world. It showed that energy itself has a granular structure at the smallest scales. This insight paved the way for technologies like lasers, LEDs, and solar cells, all of which depend on the precise control of photon energies and interactions. Light pressure is real and can push objects through space. Although photons have no mass, they carry momentum, and when they strike an object, they exert a tiny but measurable force. This radiation pressure is incredibly weak for everyday light sources, but it becomes significant in space where there's no air resistance to overcome. Solar sails represent one of the most elegant applications of light pressure. These spacecraft use large, reflective surfaces to catch sunlight and convert it into thrust. While the acceleration is gentle, it's continuous and requires no fuel. Given enough time, a solar sail can reach impressive speeds, making it an attractive option for long-distance space missions. Radiation pressure also plays important roles in astronomical phenomena. In massive stars, the outward pressure of light helps balance the inward pull of gravity. When stars near the end of their lives, this delicate balance can shift, leading to dramatic stellar winds that blow material into space at thousands of kilometers per second. The speed of light sets the ultimate limit for information transfer. In our interconnected world, we often think of communication as instantaneous, but every signal must respect this cosmic speed limit. Even electrical signals in wires travel slower than light in vacuum, though they can approach significant fractions of light speed in good conductors. This limitation becomes noticeable in global communications and space exploration. Signals to Mars can take anywhere from 4 to 24 minutes each way, depending on the planet's positions. Conversations with astronauts on the Moon involve a noticeable delay of about 1.5 seconds each way. These delays remind us that even our most advanced technologies must work within the constraints of fundamental physics. Future technologies may push closer to this limit, but they can never exceed it. Quantum entanglement, often misunderstood as faster than light communication, doesn't actually allow information transfer faster than light. The universe seems determined to maintain causality and preserve the logical flow of cause and effect. Different colors of light travel at the same speed in vacuum, but at different speeds through materials. This variation in speed for different wavelengths is called dispersion, and it's responsible for many beautiful optical phenomena. When white light passes through a prism, it separates into a rainbow because each color bends by a different amount. This same principle explains why we see rainbows after storms. Water droplets in the air act like tiny prisms, separating sunlight into its component colors. The precise angles and wavelengths create the familiar arc of colors we've admired since childhood. Each rainbow is actually a perfect demonstration of how light speed varies with wavelength in different materials. Dispersion also affects how we design optical instruments. Telescope makers must carefully account for how different colors focus at slightly different points. Camera lenses use multiple glass elements with different dispersive properties to bring all colors into sharp focus. Understanding these speed variations allows us to create instruments that reveal the universe in stunning clarity. Light can travel through materials in surprising ways. While we typically think of materials as either transparent or opaque, the reality is much more nuanced. Some materials are transparent to certain wavelengths while blocking others completely. Glass that appears perfectly clear to visible light can be opaque to infrared or ultraviolet radiation. This selective transmission has practical applications in everything from sunglasses to greenhouse design. Some materials can even guide light along curved paths, bending it around corners through total internal reflection. Fiber optic cables use this principle to carry light signals across vast distances with minimal loss, enabling the global internet infrastructure we depend on daily. Metamaterials, artificially structured materials with properties not found in nature, can manipulate light in even more exotic ways. Scientists have created materials with negative refractive indices, making light bend in the wrong direction. These discoveries open possibilities for invisibility cloaks and perfect lenses that could revolutionize optical technology. The speed of light determines how we perceive the colors around us. Every hue you see, from the deep red of a sunset to the brilliant blue of a clear sky, corresponds to light waves oscillating at specific frequencies. Red light vibrates more slowly, completing fewer cycles per second, while blue light oscillates rapidly, packing more energy into each photon. This relationship between frequency and color creates the entire visible spectrum that paints our world. What's remarkable is that these frequency differences are incredibly small on a cosmic scale, yet they create the rich visual tapestry of our daily experience. The frequency range our eyes can detect spans less than 1 octave, a tiny sliver of the vast electromagnetic spectrum. Beyond red lies infrared radiation carrying heat from warm objects. Beyond blue stretches ultraviolet light, invisible to us but capable of causing sunburns and powering photosynthesis in plants. This narrow window of perception shaped our evolution. Our eyes develop sensitivity to the wavelengths that penetrate Earth's atmosphere most effectively, the same wavelengths our sun emits most abundantly. We are, in a very real sense, creatures of light, adapted to read the universe through this particular frequency range that travels at the same fundamental speed through empty space. Light creates interference patterns that reveal its wave nature. When two light waves meet, they can either reinforce each other, creating brightness, or cancel each other out, producing darkness. This interference happens everywhere, though we rarely notice it. The shimmer on soap bubbles, the colors in oil slicks, and the patterns in peacock feathers all result from light waves interacting with themselves. These interference effects become most apparent in carefully controlled experiments. When scientists shine light through two narrow slits, they create a pattern of alternating bright and dark bands. This pattern emerges because light waves from each slit arrive at different points, with different phases, sometimes reinforcing, sometimes canceling. The result is a map of light's wave-like behavior, written in bands of illumination. This wave interference has practical applications in technologies we use every day. The anti-reflective coatings on eyeglasses work by creating destructive interference that cancels reflected light. Holography uses interference patterns to store three-dimensional images in flat surfaces. Even the operation of some lasers depends on carefully controlled interference between light waves bouncing back and forth in optical cavities. Light can exist in states of perfect coherence. Most light sources produce waves that oscillate randomly, with different parts of the beam having no fixed relationship to each other. But under special conditions, light can achieve coherence, where all the waves march in perfect synchronization. Laser light represents the ultimate expression of this coherence, with billions of photons moving in lockstep. This coherence gives lasers their unique properties. Coherent light can travel vast distances without spreading out, maintain its intensity over long paths, and interfere with itself in predictable ways. These characteristics make lasers invaluable for everything from surgery to manufacturing to measuring the distance to the moon with incredible precision. The quest for coherent light led to some of the most sophisticated technologies ever developed. Creating a laser requires precise control over atoms and electrons, forcing them to emit light in coordination rather than randomly. The process reveals the deep quantum mechanical nature of light emission and absorption, showing how individual atomic events can be orchestrated into collective behavior. Polarization gives light a hidden dimension of orientation. Light waves oscillate perpendicular to their direction of travel, but they can vibrate in any orientation around that direction. This property, called polarization, remains invisible to our eyes, but profoundly affects how light interacts with materials and other light waves. Polarized sunglasses take advantage of this hidden property. They contain filters that block light vibrating in certain orientations while allowing others to pass through. This selective filtering reduces glare from horizontal surfaces like water or pavement, where reflected light tends to become horizontally polarized. The result is clearer vision and reduced eye strain in bright conditions. Polarization also plays crucial roles in biology and technology. Some insects navigate using patterns of polarized light in the sky, invisible landmarks that help them find their way home. LCD displays control light polarization to create images, twisting liquid crystals to either block or transmit light at each pixel. These applications reveal another layer of light's complexity, hidden from casual observation, but essential to understanding its complete nature. The electromagnetic spectrum extends far beyond visible light. What we call light is actually just a small portion of a vast family of electromagnetic radiation, all traveling at the same speed but with different wavelengths and energies. Radio waves stretch for kilometers from crest to crest, while gamma rays have wavelengths smaller than atomic nuclei. Each part of this spectrum interacts differently with matter, creating unique possibilities for science and technology. Radio waves pass easily through walls and atmosphere, making them ideal for communication. Microwaves are absorbed by water molecules, heating food from the inside out. X-rays penetrate soft tissue but are blocked by bones, creating medical images that reveal internal structures. The unity of electromagnetic radiation was one of the great discoveries of 19th century physics. Scientists realized that light, radio waves, and all the rest were manifestations of the same fundamental phenomenon, differing only in frequency and wavelength. This understanding unified seemingly separate areas of science and opened up the entire electromagnetic spectrum for human use and exploration. Light exhibits phenomena that challenge our everyday understanding of reality. Quantum mechanics reveals that individual photons can take multiple paths simultaneously, existing in what physicists call superposition. This isn't just mathematical abstraction. Experiments consistently show that single photons interfere with themselves, creating patterns that only make sense if each particle somehow explores all possible routes. This quantum behavior becomes even stranger when we consider entanglement. Two photons can become connected in such a way that measuring one instantly affects the other, regardless of the distance between them. Einstein called this spooky action at a distance, but experiments have confirmed that entangled photons maintain their connection even when separated by continents. These quantum properties of light aren't just laboratory curiosities. They form the foundation for emerging technologies like quantum computing and quantum cryptography. These systems use light's quantum nature to perform calculations and secure communications in ways that would be impossible with classical physics. The strange world of quantum optics is slowly becoming the practical world of quantum technology. Light pressure shapes the structure of the universe itself. Though incredibly weak by everyday standards, radiation pressure becomes significant in extreme astronomical environments. In the most massive stars, the outward pressure of light helps support the star against gravitational collapse. This delicate balance between radiation pressure and gravity determines how long stars live and how they die. When massive stars explode as supernovae, radiation pressure plays a dramatic role in blowing away the star's outer layers. The explosion creates light so intense that its pressure can accelerate material to thousands of kilometers per second. These stellar winds, driven by light pressure, enrich the surrounding space with heavy elements forged in the star's core. On smaller scales, radiation pressure affects the formation and evolution of planetary systems. It can blow away dust and gas from around young stars, clearing space for planets to form. It also influences the orbits of small particles and spacecraft, creating subtle but measurable effects that mission planners must account for when navigating through the solar system. The speed of light creates a fundamental relationship between energy and mass. Einstein's most famous equation reveals that mass and energy are interchangeable, with light speed serving as the conversion factor. This relationship isn't just theoretical. It explains why the sun shines, how nuclear reactors work, and why particle accelerators can create new forms of matter from pure energy. Every chemical reaction, every biological process, and every stellar fusion involves tiny conversions between mass and energy at the rate determined by light speed squared. The enormous value of this conversion factor means that small amounts of mass correspond to tremendous quantities of energy. This is why nuclear processes release so much more energy than chemical ones. Understanding this mass-energy relationship opened both opportunities and challenges for humanity. It revealed the source of stellar energy, explaining how stars can shine for billions of years. It also made possible both nuclear power and nuclear weapons, technologies that continue to shape our world in profound ways. Light carries momentum despite having no mass. This apparent contradiction puzzled early physicists, but quantum mechanics resolved the paradox. Photons possess momentum proportional to their energy, even though they have no rest mass. This momentum becomes apparent when light interacts with matter, transferring its motion to whatever absorbs or reflects it. The momentum of light enables technologies like optical tweezers, which use focused laser beams to trap and manipulate microscopic objects. By carefully controlling the light's intensity and focus, scientists can grab individual cells or molecules, moving them around like tiny tools. This technique has revolutionized biology and nanotechnology, allowing researchers to study single molecules and assemble structures atom by atom. Solar radiation pressure also affects spacecraft navigation in subtle but important ways. Over long missions, the gentle push of sunlight can alter a spacecraft's trajectory by surprising amounts. Mission controllers have learned to use this effect to their advantage, adjusting spacecraft orientation to harness light pressure for course corrections, saving fuel for other maneuvers. Time itself dilates as speeds approach that of light. This isn't science fiction, but established physics, confirmed in countless experiments. As objects move faster, time passes more slowly for them relative to stationary observers. At light speed, time would stop completely, though nothing with mass can actually reach this limit. This time dilation affects particles created in cosmic ray collisions high in Earth's atmosphere. These particles have such short lifetimes that they should decay before reaching the ground. Yet detectors consistently observe them at sea level because their high-speed journey stretches their lifetimes from our perspective. Time dilation turns particles that should live for microseconds into cosmic messengers that survive long enough to reach our instruments. The relationship between speed and time creates a fundamental asymmetry in the universe. There's no upper limit to how slowly time can pass, but there's an absolute ceiling set by light speed. This asymmetry shapes everything from the design of particle accelerators to our understanding of black holes, where time dilation reaches extreme proportions near the event horizon. Light's journey through the universe tells the story of cosmic evolution. The oldest light we can observe, the cosmic microwave background, shows us the universe as it appeared when it first became transparent to radiation. Before this epoch, the cosmos was so hot and dense that light couldn't travel far without being absorbed and re-emitted by free electrons. When the universe cooled enough for atoms to form, light suddenly found itself free to travel across vast distances. This liberation created the cosmic microwave background, a snapshot of the universe at 380,000 years old. By studying the subtle patterns in this ancient light, cosmologists can map the seeds of structure that eventually grew into galaxies and stars. The light from the first stars and galaxies also carries information about cosmic dawn, the period when the universe emerged from its dark ages. Telescopes like the James Webb Space Telescope can detect this ancient starlight, red shifted by cosmic expansion into infrared wavelengths. Each photon from these distant sources is a messenger from the early universe, carrying news of how cosmic structure first began to form. The speed of light defines the very fabric of causality itself. Without this cosmic speed limit, cause and effect would become meaningless concepts. Events could influence their own past, creating paradoxes that would unravel the logical structure of reality. The universe seems to enforce this limit not merely as a constraint on motion, but as a fundamental principle that preserves the arrow of time and maintains the coherent flow of existence. This relationship between light speed and causality becomes most apparent when we consider information transfer. No signal, no influence, no effect can propagate faster than light through space. This creates what physicists call light cones, geometric regions that define which events can influence each other. The past light cone contains all events that could have affected a given moment, while the future light cone encompasses everything that moment might influence. These limitations aren't merely theoretical. They shape how we understand everything from quantum mechanics to the expansion of the universe. Even in the strangest quantum phenomena, where particles seem to affect each other instantaneously across vast distances, no actual information travels faster than light. The universe maintains its logical consistency by preserving this fundamental speed barrier. Light exhibits behaviors that seem to violate our intuitions about waves and particles. When scientists fire individual photons through a double-slit apparatus one at a time, something remarkable happens. Each photon somehow passes through both slits simultaneously, interfering with itself to create the familiar pattern of bright and dark bands. This occurs even when photons are emitted so rarely that only one exists in the apparatus at any given moment. The mystery deepens when we try to observe which slit each photon actually uses. The moment we place detectors to monitor the photon's path, the interference pattern vanishes. The photon begins behaving like a classical particle, passing through one slit or the other, but never both. This isn't a limitation of our measurement tools, it's a fundamental feature of quantum reality that reveals the strange relationship between observation and physical behavior. This wave-particle duality extends beyond individual photons to entire beams of light. Laser light can exhibit both wave-like and particle-like properties simultaneously, depending on how we choose to observe it. The choice of measurement determines which aspect of light's nature becomes apparent. suggesting that reality itself may be more fluid than our everyday experience suggests. Light interacts with gravity in ways that reshape our understanding of space and time. Massive objects bend the fabric of space-time, creating curved paths that light must follow. This gravitational lensing effect turns distant galaxies into cosmic magnifying glasses, allowing astronomers to peer deeper into the universe than would otherwise be possible. The bending of light by gravity isn't just a theoretical curiosity. It was one of the first experimental confirmations of Einstein's general theory of relativity. During a solar eclipse in 1919, astronomers observed stars appearing in slightly different positions as their light curved around the sun's gravitational field. This subtle shift in stellar positions provided dramatic evidence that gravity affects light itself. Black holes represent the extreme limit of gravitational light bending. At the event horizon, space-time curves so severely that light can no longer escape. The speed of light remains constant even here, but the geometry of space itself becomes so distorted that all paths lead inward. Light trapped at the event horizon neither advances nor retreats, frozen in a timeless dance at the edge of ultimate darkness. The interaction between light and matter reveals the quantum nature of both energy and atoms. When photons strike electrons in atoms, they can only transfer very specific amounts of energy. This quantized interaction explains why different elements emit and absorb light at characteristic wavelengths, creating the spectral fingerprints that allow astronomers to determine the composition of distant stars. These atomic transitions occur at precise frequencies determined by the energy levels within each atom. When an electron jumps from a higher energy level to a lower one, it emits a photon with exactly the right frequency to carry away the excess energy. The reverse process, absorption, requires a photon with precisely the correct energy to boost an electron to a higher level. This quantum relationship between light and matter enables technologies that have transformed modern life. Lasers work by forcing atoms to emit photons in perfect synchronization, creating coherent beams with remarkable properties. Solar cells convert photon energy directly into electrical current through carefully engineered quantum transitions. Even the biological process of photosynthesis relies on quantum mechanical interactions between light and molecular structures. Light pollution affects more than just our view of the stars. The artificial illumination that brightens our nights disrupts natural rhythms that evolved over billions of years. Many creatures navigate by starlight, time their reproduction by lunar cycles, and regulate their behavior according to the natural progression from day to night. Our constant artificial lighting creates confusion in these ancient systems. The problem extends beyond biology to affect human health and well-being. Our bodies evolved to respond to the natural cycle of light and darkness, using these cues to regulate sleep, hormone production, and countless other physiological processes. The blue, rich light from modern displays and LED fixtures can disrupt these circadian rhythms, affecting everything from sleep quality to immune function. Efforts to reduce light pollution reveal how profoundly artificial illumination has changed our relationship with the cosmos. In many urban areas, only the brightest stars remain visible, robbing entire generations of the experience of seeing the Milky Way stretching across a dark sky. This disconnect from the natural night sky represents a loss that extends far beyond astronomy, to touch our fundamental connection with the universe. The speed of light creates practical limitations for space exploration that no amount of technological advancement can overcome. Even if we could build spacecraft capable of reaching significant fractions of light speed, the time required for interstellar travel would span decades or centuries. This reality forces us to think about space exploration in terms of generational missions and robotic ambassadors rather than quick round trips. Communication with distant spacecraft faces the same fundamental constraints. Commands sent to probes exploring the outer solar system take hours to arrive, and responses take just as long to return. Mission controllers must plan operations with these delays in mind, programming spacecraft to make autonomous decisions when immediate human guidance isn't possible. These limitations also affect our search for extraterrestrial intelligence. Radio signals from the nearest potentially habitable planets would take years to reach us, and any response would take just as long to return. A conversation with alien civilizations would unfold over decades, requiring patience and commitment that spans generations. The speed of light ensures that contact with other worlds would be a slow, deliberate process rather than the instant communication we might imagine. Light's behavior in extreme environments reveals physics at its most fundamental level. In the intense magnetic fields around neutron stars, light can split into multiple polarizations, each following slightly different paths through the twisted space-time. These effects provide natural laboratories for testing our understanding of both quantum mechanics and general relativity under conditions impossible to recreate on Earth. The collision of black holes creates ripples in space-time itself, gravitational waves that carry information about these cosmic catastrophes at light speed. When these waves pass through Earth, they stretch and compress space by amounts smaller than a proton's width. Detecting these infinitesimal changes required some of the most sensitive instruments ever built, capable of measuring distortions that would be imperceptible even to atoms. These gravitational wave discoveries have opened an entirely new window on the universe. Unlike light, gravitational waves can pass through matter almost unimpeded, carrying information from the most extreme events in cosmic history. They allow us to observe phenomena that remain invisible to traditional telescopes, from the merger of black holes to the collapse of massive stars into neutron stars. The relationship between light and consciousness remains one of science's deepest mysteries. Our perception of color, brightness, and visual beauty emerges from electrochemical signals, triggered by photons striking specialized cells in our retinas. Yet somehow this biological machinery gives rise to the rich, subjective experience of seeing a sunset or recognizing a loved one's face. The processing of visual information involves intricate networks of neurons that analyze everything from motion and edges to faces and spatial relationships. Different wavelengths of light activate different types of cone cells, creating the neural basis for color vision. But how these objective, measurable processes transform into subjective, conscious experience remains unexplained. This mystery extends beyond human vision to the broader question of how any physical system can give rise to awareness and experience. Light provides the primary channel through which we gather information about our world, yet the transformation of photons into consciousness involves processes we're only beginning to understand. In studying light, we inevitably encounter the deepest questions about the nature of mind and experience. Light enables communication across the cosmos through a universal language of physics. The same electromagnetic radiation that illuminates our world also carries signals from distant civilizations if they exist. Radio telescopes scan the sky for artificial patterns that might indicate intelligent origin, searching for the technological signatures of other worlds. The search for extraterrestrial intelligence relies on the assumption that any advanced civilization would eventually discover radio waves and other forms of electromagnetic radiation. These signals travel at light speed across interstellar distances, potentially carrying messages, entertainment, or simply the inadvertent electromagnetic noise of technological societies. The vastness of space and the limited speed of light mean that such communications would represent conversations across time as much as distance. A signal detected from a star system 100 light-years away would show us that civilization as it existed a century ago. By the time we could respond, another century would pass before our reply could arrive. These cosmic conversations would unfold across multiple human generations. The quantum nature of light continues to surprise scientists with behaviors that challenge classical intuitions. Photons can become entangled with each other, sharing quantum states across arbitrary distances. When the quantum state of one entangled photon is measured, its partner instantly assumes a correlated state, regardless of the space between them. This quantum entanglement doesn't violate the speed of light limit because no information actually travels between the particles. Instead, they share a quantum correlation that was established when they were created together. The measurement reveals pre-existing correlations rather than transmitting new information, preserving causality while demonstrating the non-local nature of quantum mechanics. These entangled photons have practical applications in quantum cryptography, where they can create unbreakably secure communication channels. Any attempt to intercept quantum encrypted messages would disturb the entangled photons, revealing the presence of eavesdroppers. This technology promises to revolutionize secure communication by using the fundamental properties of light to guarantee privacy. The study of light has driven some of the most important technological advances in human history. From the simple lens that first magnified text for aging eyes to the complex laser systems that enable modern surgery, our understanding of light's behavior has consistently translated into practical benefits. Each new insight into light's nature has opened possibilities that previous generations couldn't imagine. The development of fiber optic communication demonstrates how fundamental research into light's properties can transform society. The ability to guide light through glass fibers with minimal loss enabled the global internet infrastructure we depend on today. Information travels through these glass pathways at nearly the speed of light, connecting distant continents in fractions of a second. Future technologies based on our understanding of light promise even more dramatic changes. Quantum computers using photons to process information could solve problems beyond the reach of classical computers. Light-based medical treatments might target diseases at the cellular level with unprecedented precision. Solar energy technologies continue to improve as we better understand how to capture and convert light into useful forms of power. Light reveals the quantum nature of energy in ways that transformed our understanding of the universe. When heated objects glow, they don't emit light at all wavelengths equally. Instead, they produce characteristic patterns that puzzled scientists for decades. The solution came when Max Planck proposed that energy exists in discrete packets, or quanta, rather than as a continuous flow. This revolutionary idea explained why hot objects emit specific colors at specific temperatures. The quantum nature of light becomes apparent in phenomena we encounter daily. When you take a photograph, each pixel in your camera's sensor responds to individual photons striking it. Digital cameras essentially count photons, converting these tiny packets of energy into electrical signals. The graininess you might notice in low-light photos reflects the discrete nature of light itself, each grain representing the statistical arrival of photons at different parts of the sensor. This granular structure of light energy has profound implications for how we understand the smallest scales of nature. Photons can't be divided into smaller pieces of light energy. They represent the fundamental quantum of electromagnetic radiation. Indivisible units that carry specific amounts of energy determined entirely by their wavelength or frequency. The wave nature of light creates interference patterns that reveal hidden structures throughout the universe. When astronomers observe distant stars through Earth's atmosphere, the starlight creates complex interference patterns as it passes through pockets of air at different temperatures and densities. These patterns, called speckles, contain detailed information about both the star's surface and the atmospheric conditions between us. Advanced telescopes use this interference information to reconstruct incredibly detailed images of stellar surfaces and even detect planets orbiting other stars. By analyzing how starlight interferes with itself after traveling through space and atmosphere, we can peer into cosmic details that would otherwise remain invisible. The wave nature that creates these patterns also enables holographic techniques that store three-dimensional information in flat surfaces. Interference effects also explain some of the most beautiful colors in nature. The iridescent wings of butterflies, the shimmering shells of beetles, and the brilliant plumage of hummingbirds all result from microscopic structures that create interference between reflected light waves. These biological systems achieve colors more vivid and pure than most artificial dyes or pigments. Light propagates through space as electromagnetic waves that carry both electric and magnetic fields. These fields oscillate perpendicular to each other and to the direction of travel, creating a self-sustaining wave that needs no medium to support it. Unlike sound waves, which require air or another substance to travel through, light waves generate their own support structure from the interplay of electric and magnetic forces. This electromagnetic nature of light explains why it can travel through the vacuum of space. The oscillating electric field creates a changing magnetic field, which in turn generates a changing electric field, and so on in an endless cycle that propagates at light speed. This self-supporting wave carries energy across vast distances without losing its fundamental character. The strength of these electromagnetic fields determines light's intensity, while their frequency determines its color and energy. Radio waves have the same electromagnetic nature as visible light, but their electric and magnetic fields oscillate much more slowly. X-rays and gamma rays follow the same pattern, but with much more rapid oscillations that carry far more energy per photon. Refraction bends light in ways that create both practical tools and natural wonders. When light passes from one transparent material to another, it changes speed and direction in a predictable way. This bending, called refraction, occurs because light travels at different speeds in different materials. The precise amount of bending depends on both the materials involved and the wavelength of the light. Our eyes rely on refraction to focus light onto the retina. The curved surfaces of the cornea and lens bend incoming light rays so they converge at precisely the right distance to form sharp images. When this focusing system doesn't work perfectly, we experience nearsightedness, farsightedness, or astigmatism. Corrective lenses use carefully calculated refraction to restore proper focus. Atmospheric refraction creates some of nature's most spectacular optical displays. Mirages form when light bends through air layers at different temperatures, making distant objects appear displaced or duplicated. The green flash, sometimes visible at sunset, results from atmospheric refraction, separating sunlight into its component colors. Even the apparent position of stars shifts slightly due to refraction through Earth's atmosphere. Total internal reflection traps light within materials under specific conditions. When light tries to pass from a denser material to a less dense one at too shallow an angle, it reflects completely back into the denser material. This phenomenon enables fiber optic cables to guide light signals around corners and across continents with minimal loss. The critical angle for total internal reflection depends on the properties of both materials. Diamond has such a high refractive index that light entering it becomes trapped easily, bouncing around inside the gem and creating the brilliant sparkle we associate with fine jewelry. This same principle allows light to travel through bent glass fibers, following curved paths that would be impossible for light traveling through air. Nature uses total internal reflection in surprising ways. Some deep-sea creatures have evolved light guides within their bodies, channeling bioluminescent light to specific locations for communication or hunting. Certain plants use internal reflection to distribute sunlight more efficiently throughout their leaves, maximizing photosynthesis even in low light conditions. Scattering explains why the sky appears blue and sunsets glow red. When light encounters particles smaller than its wavelength, it scatters in all directions. Blue light, with its shorter wavelength, scatters more strongly than red light when it interacts with the tiny molecules in Earth's atmosphere. This preferential scattering of blue light fills our sky with azure hues during the day. At sunrise and sunset, sunlight must travel through much more atmosphere to reach us. This extended journey scatters away most of the blue light, leaving the longer wavelengths of red and orange to paint the sky in warm colors. The same scattering that creates blue skies during the day produces the golden hour light that photographers prize for its warm, soft quality. Different sized particles create different scattering effects. Larger particles like dust and water droplets scatter all colors more equally, which is why clouds appear white or gray rather than blue. Extremely small particles can create more exotic scattering effects, such as the brilliant colors sometimes seen in thin clouds near the sun. The Doppler effect shifts light wavelengths when sources move relative to observers. Just as the pitch of a siren changes as an ambulance passes by, light from moving objects shifts toward shorter or longer wavelengths depending on whether the source approaches or recedes. This Doppler shift provides astronomers with a powerful tool for measuring cosmic motions. Stars orbiting each other create periodic Doppler shifts in their light as they alternately approach and recede from Earth during their orbital dance. These shifts reveal the presence of companion stars too dim to see directly and allow astronomers to measure orbital periods and distances. Many exoplanets were first discovered through the tiny Doppler shifts they create in their parent star's light. The expansion of the universe creates a cosmological redshift that stretches light from distant galaxies toward longer, redder wavelengths. The farther away a galaxy lies, the more its light has been stretched by cosmic expansion during its journey to Earth. This relationship between distance and redshift provided the first evidence that the universe is expanding and continues to accelerate. Absorption and emission lines create cosmic fingerprints that reveal the composition of distant objects. When light passes through cooler gas, atoms absorb photons at very specific wavelengths, creating dark lines in what would otherwise be a continuous spectrum. Conversely, hot gases emit light at characteristic wavelengths, producing bright emission lines. Each chemical element produces its own unique pattern of absorption and emission lines, like a barcode that identifies its presence in distant stars and galaxies. By analyzing these spectral lines, astronomers can determine not only what elements exist in far-off objects, but also their temperatures, densities, and motions through space. These spectral fingerprints revealed that the universe contains the same chemical elements everywhere, from nearby stars to the most distant galaxies. This universality suggests that the fundamental laws of physics operate consistently throughout the cosmos, making astronomical observations relevant to our understanding of matter and energy in general. Lasers represent the ultimate expression of light's coherent nature. Unlike ordinary light sources that emit photons randomly, lasers produce light where all the photons march in perfect step, sharing the same wavelength, phase, and direction. This coherence gives laser light remarkable properties that have revolutionized fields from medicine to manufacturing. The process of creating laser light requires precise control over atomic energy levels. Atoms must be excited to higher energy states and then stimulated to emit photons in exactly the same way. This stimulated emission creates a cascade effect where each emitted photon triggers the emission of additional identical photons, building up intense, coherent beams. Different materials produce lasers at different wavelengths, from infrared through visible light to ultraviolet. Gas lasers, solid-state lasers, and semiconductor lasers each use different physical mechanisms to achieve population inversion and stimulated emission. The specific wavelength and power characteristics of each type make them suitable for different applications, from delicate eye surgery to cutting through thick metal plates. Fluorescence and phosphorescence demonstrate how atoms interact with light energy. When certain materials absorb light, their electrons jump to higher energy levels. As these electrons return to their ground states, they emit light at wavelengths that depend on the specific energy gaps within each atom or molecule. This process can create colors completely different from the original illumination. Fluorescent materials emit light immediately after absorbing it, creating brilliant colors under ultraviolet illumination. Many flowers, minerals, and marine organisms exhibit fluorescence, often serving biological functions like attracting pollinators or confusing predators. Fluorescent lighting uses this principle to convert ultraviolet radiation into visible light efficiently. Phosphorescent materials store absorbed energy temporarily, releasing it slowly as a gentle glow that can persist for hours after the exciting light source is removed. This delayed emission creates the glow in the dark effects used in safety signs and novelty items. Some deep sea creatures use bioluminescent versions of phosphorescence to create living light sources in the ocean's depths. Light therapy harnesses specific wavelengths to trigger biological responses in living tissues. Different colors of light penetrate to different depths in skin and interact with various cellular components. Red and near-infrared light can stimulate cellular metabolism and promote healing, while blue light can kill certain bacteria and treat some skin conditions. Seasonal affective disorder responds to bright light therapy that helps regulate circadian rhythms disrupted by reduced daylight during winter months. The timing, intensity, and spectrum of light exposure can significantly affect mood, sleep patterns, and overall well-being. This demonstrates how deeply our biology remains connected to natural light cycles. Photodynamic therapy combines specific wavelengths of light with light-sensitive drugs to treat certain cancers and other conditions. The drugs accumulate preferentially in diseased tissues, then become toxic when activated by precisely tuned laser light. This approach allows targeted treatment that minimizes damage to healthy surrounding tissues. Nonlinear optics reveals how intense light can change the properties of materials it passes through. When extremely bright laser light interacts with certain crystals, it can double its frequency, converting red light to green or green light to blue. These frequency doubling effects only occur when light intensities become high enough to significantly disturb the electrons within the material. These nonlinear effects enable the creation of laser light at wavelengths that would be difficult or impossible to generate directly. Many green laser pointers actually contain infrared lasers coupled with frequency doubling crystals that convert the invisible infrared light into visible green beams. More exotic nonlinear effects can create entirely new colors of light through processes like four-wave mixing and stimulated Raman scattering. These phenomena demonstrate that light itself can serve as a tool for manipulating the properties of matter, opening possibilities for all optical signal processing and computation. Metamaterials artificially structured at scales smaller than light wavelengths can manipulate electromagnetic radiation in ways not found in natural materials. By arranging conducting elements in precise patterns, engineers can create materials with negative refractive indices, perfect absorption, or other exotic optical properties. These engineered materials could enable invisibility cloaks that guide light around objects, making them essentially transparent to observation. Perfect lenses that overcome the diffraction limit might allow optical microscopy at unprecedented resolution. Metamaterials also promise more efficient solar cells and antennas that could revolutionize energy harvesting and wireless communication. The field of transformation optics uses metamaterials to control light flows as precisely as engineers control water through pipes and channels. This capability could lead to optical computers that process information at light speed, using photons instead of electrons for computation and data storage. Optical illusions reveal how our brains interpret light patterns and can be fooled by clever arrangements of color and contrast. These visual tricks demonstrate that perception involves active processing rather than passive recording of light patterns. Our visual system makes assumptions about lighting, depth, and motion that can be exploited to create seemingly impossible images. Understanding these perceptual processes helps explain not only how optical illusions work, but also how normal vision functions. The brain constantly interprets ambiguous visual information, filling in gaps and making educated guesses about the three-dimensional world based on the two-dimensional patterns of light that reach our retinas. These same principles influence art, architecture, and design. artists have long used knowledge of how we perceive light and shadow to create convincing illusions of depth and form on flat surfaces. Modern displays use sophisticated understanding of human color perception to create convincing images using just 3 primary colors. The study of light continues to push the boundaries of what we thought possible in physics and technology. Researchers work to slow light to a complete stop, trap it in crystalline structures, and even reverse its direction of travel. These exotic manipulations of light could enable quantum memory devices that store information in photons themselves. Quantum dots, tiny semiconductor particles, can be tuned to emit very precise colors by controlling their size at the atomic level. These engineered light emitters promise more efficient displays, better solar cells, and new types of biological markers that could revolutionize medical imaging and treatment. As we probe deeper into light's mysteries, each discovery opens new questions and possibilities. The simple concept of electromagnetic radiation traveling at a fixed speed through space has evolved into a rich understanding of quantum fields, space-time geometry, and the fundamental nature of information and reality itself. Light continues to illuminate not just our physical world, but our understanding of existence at its most basic level. The speed of light imposes fundamental limits on how quickly information can propagate through the universe. This constraint affects everything from the design of computer processors to the coordination of global financial markets. Even electrical signals in computer circuits travel at only a fraction of light speed, creating timing challenges that engineers must carefully consider when designing high-performance systems. In quantum mechanics, the speed of light sets the boundary between cause and effect on the smallest scales. Virtual particles, the quantum fluctuations that fill empty space, must respect this cosmic speed limit in their brief existence. These ephemeral entities can borrow energy from the vacuum, but only for time so short that light cannot travel far enough to violate causality. The relationship between light speed and information becomes particularly intriguing when we consider quantum entanglement. While entangled particles appear to influence each other instantly across any distance, no usable information actually travels between them faster than light. This preserves the logical structure of space-time while allowing for the strange correlations that make quantum mechanics so mysterious and powerful. Light exhibits behaviors in materials that seem to defy its fundamental nature. In photonic crystals, carefully arranged structures can create forbidden zones where certain wavelengths of light cannot propagate at all. These materials act like semiconductors for light, controlling photon flow with the same precision that electronic semiconductors control electron movement. Slow light phenomena in these engineered materials can reduce light speed to mere meters per second, slower than a walking pace. Scientists have even achieved negative group velocities, where light pulses appear to exit a material before they fully enter it. These effects don't violate relativity because no information travels faster than light, but they reveal the complex relationship between wave propagation and information transfer. Such exotic light manipulation could enable all optical computers that process information using photons instead of electrons. These systems might operate at unprecedented speeds while consuming far less energy than traditional electronic computers. The ability to stop, store, and release light on command could revolutionize how we handle and process information. Bioluminescence demonstrates how living organisms have evolved to generate light through chemical reactions, from fireflies flashing in summer meadows to deep-sea creatures creating their own illumination in the ocean's depths. Biological light production serves purposes ranging from communication to predation. These living light sources achieve remarkable efficiency, converting chemical energy to light with minimal heat production. The biochemistry of bioluminescence involves specialized molecules called luciferins that react with oxygen in the presence of enzymes called luciferases. This reaction produces photons directly, bypassing the heat generation that makes artificial light sources inefficient. Some organisms can control their light production with precise timing, creating complex signaling patterns for mating displays or territorial communication. Marine bioluminescence creates some of the ocean's most spectacular displays. Dinoflagellates produce sparkling blue light when disturbed, creating trails of living stars behind swimming fish or boats. Deep-sea anglerfish use bioluminescent lures to attract prey in the perpetual darkness of the deep ocean. These biological light sources demonstrate the fundamental importance of photons in the web of life. The interaction between light and biological systems reveals the quantum nature of photosynthesis. Plants capture solar energy with remarkable efficiency through quantum coherence effects that allow energy to explore multiple pathways simultaneously. This quantum behavior helps photosynthetic systems find the most efficient route for energy transfer, maximizing the conversion of sunlight into chemical energy. Recent research suggests that quantum effects in photosynthesis persist even at warm temperatures and in the presence of biological noise. This challenges traditional assumptions about when quantum mechanics becomes relevant in biological systems. The discovery that life itself uses quantum coherence to harvest light energy has inspired new approaches to artificial photosynthesis and solar energy conversion. These biological quantum effects demonstrate that the strange behaviors of light observed in physics laboratories also operate in living systems. Evolution has apparently discovered and exploited quantum mechanics long before humans understood these phenomena. This suggests that quantum effects may be more widespread in biology than previously recognized. Light's interaction with atmospheric particles creates the aurora, one of nature's most magnificent displays. When charged particles from the solar wind collide with Earth's magnetic field, they spiral down magnetic field lines toward the poles. These high-energy particles excite atoms and molecules in the upper atmosphere, causing them to emit light at characteristic wavelengths. Oxygen atoms produce the green and red colors most commonly seen in auroral displays, while nitrogen contributes blue and purple hues. The specific colors depend on the altitude where collisions occur and the energy of the incoming particles. These celestial light shows can stretch across hundreds of kilometers of sky, rippling and dancing as the solar wind varies in intensity. The aurora provides a visible reminder of the constant interaction between our planet and the space environment around it. The magnetic field that protects us from harmful solar radiation also channels some particles into our atmosphere, creating these beautiful displays. Similar auroral phenomena occur on other planets with magnetic fields, including Jupiter and Saturn. Fiber optic technology transforms light into the backbone of global communication. Hair-thin glass fibers can carry thousands of separate light signals simultaneously, each at a different wavelength, through a technique called wavelength division multiplexing. These optical highways carry internet traffic, telephone calls, and data streams across continents at nearly the speed of light. The purity of optical fibers approaches theoretical limits, allowing light signals to travel hundreds of kilometers before requiring amplification. Specially designed fibers can maintain signal quality across transoceanic distances, connecting continents through undersea cables that form the physical foundation of the global internet. These glass pathways carry the majority of international communications traffic. Advances in fiber optic technology continue to increase data transmission capacity. New types of fibers can carry even more information by using different modes of light propagation, or by managing the polarization of optical signals. These developments help meet the ever-growing demand for bandwidth in our increasingly connected world. Light pollution represents an unintended consequence of artificial illumination that affects both astronomy and biology. The glow from cities can be seen from space, creating vast domes of light that obscure the natural night sky. This artificial brightness disrupts the circadian rhythms of many species and makes astronomical observations increasingly difficult. Efforts to reduce light pollution focus on using more efficient lighting that directs illumination only where needed. Full cutoff fixtures prevent light from scattering upward into the sky, while better timing controls reduce unnecessary nighttime lighting. These measures can significantly reduce energy consumption while preserving the natural darkness that many species require. The loss of dark skies represents more than just an inconvenience for astronomers. Throughout human history, the night sky has inspired art, religion, and scientific curiosity. Many urban dwellers today have never seen the Milky Way clearly, losing connection with the cosmic context that shaped human culture for millennia. Preserving dark sky areas becomes increasingly important as urbanization spreads. Optical computing promises to revolutionize information processing by using photons instead of electrons. Light-based processors could operate at much higher speeds than electronic circuits while generating less heat. Optical switches can redirect light beams in fractions of a nanosecond, enabling parallel processing architectures impossible with conventional electronics. The challenge in optical computing lies in creating practical optical logic gates and memory elements. While light excels at carrying information over long distances, manipulating optical signals for computation requires sophisticated materials and precise control. Researchers explore various approaches from using nonlinear optical effects to hybrid systems that combine optical and electronic components. Quantum optical computing takes these concepts even further, using individual photons to carry quantum information. These systems could solve certain types of problems exponentially faster than classical computers. The manipulation of quantum states of light offers possibilities for computation that transcend the limitations of classical physics. Holography captures and reconstructs three-dimensional light fields with remarkable fidelity. Unlike conventional photography, which records only the intensity of light, holography preserves both intensity and phase information. This complete recording of light waves allows the reconstruction of images that appear truly three-dimensional, changing perspective as the viewer moves. The principles of holography extend beyond creating three-dimensional images. Holographic data storage can record information throughout the volume of a material rather than just on its surface, potentially increasing storage density by orders of magnitude. Holographic techniques also enable advanced microscopy methods that can see through opaque materials or reconstruct images from scattered light. Digital holography combines these optical principles with electronic processing to create dynamic three-dimensional displays. These systems could eventually replace flat screens with true volumetric displays that present information in three-dimensional space. Such displays might revolutionize fields ranging from medical imaging to engineering design. The cosmic microwave background radiation provides a snapshot of the universe when it first became transparent to light. This ancient radiation, released when the cosmos was only 380,000 years old, carries detailed information about the early universe's structure and composition. Tiny variations in this background light reveal the seeds that eventually grew into galaxies and stars. Studying this primordial light requires sophisticated instruments capable of detecting minute temperature differences across the sky. Satellite missions have mapped these variations with extraordinary precision, revealing patterns that confirm our understanding of cosmic inflation and dark matter. Each photon from this ancient era is a messenger from the universe's infancy. The polarization patterns in the cosmic microwave background could reveal even more secrets about the early universe. These subtle signatures might provide evidence of gravitational waves from cosmic inflation, or reveal details about the fundamental physics operating in the universe's first moments. Future missions will search for these faint signals in the ancient light. Adaptive optics corrects for atmospheric turbulence in real time, allowing ground-based telescopes to achieve image quality rivaling space-based instruments. These systems use deformable mirrors that change shape hundreds of times per second to compensate for the blurring effects of Earth's atmosphere. The result is dramatically sharper images of celestial objects. The technology behind adaptive optics requires precise measurement of atmospheric distortions using guide stars or laser beacons. Computer-controlled actuators then reshape telescope mirrors to cancel out these distortions before they can blur the final image. This real-time correction allows astronomers to peer deeper into space with unprecedented clarity. Adaptive optics has applications beyond astronomy. Similar techniques are being developed for laser surgery, where atmospheric or tissue turbulence can affect beam quality. Industrial applications include laser manufacturing processes that require precise beam shaping and focusing over long distances. Light carries angular momentum in addition to energy and linear momentum. Circularly polarized light possesses spin-angular momentum, while specially structured beams can carry orbital angular momentum through their twisted wavefronts. These rotational properties of light can be transferred to matter, creating new tools for manipulation at microscopic scales. Optical tweezers exploit these momentum transfer effects to trap and manipulate individual particles using focused laser beams. By carefully controlling the intensity and phase structure of light, scientists can create optical traps that hold microscopic objects in three-dimensional space. These tools enable precise manipulation of individual cells, molecules, and even atoms. The orbital angular momentum of light offers new possibilities for information encoding. Twisted light beams can carry additional channels of information beyond conventional amplitude and frequency modulation. This could increase the capacity of optical communication systems and enable new types of quantum information processing. Metamaterials with negative refractive indices bend light in ways not found in natural materials. These artificially structured materials can focus light to spots smaller than its wavelength or create perfect lenses that overcome traditional optical limitations. The unusual properties emerge from the precise arrangement of conducting elements at scales smaller than the wavelength of light. Cloaking devices based on transformation optics use metamaterials to guide light around objects, rendering them essentially invisible to observation. While perfect invisibility remains challenging, these materials can reduce scattering and reflection significantly. The same principles might enable perfect absorbers that trap light completely, or antennas with unprecedented directional control. The development of metamaterials pushes the boundaries of what materials can do to light. By engineering structure at the nanoscale, researchers can create optical properties that exceed those of any natural substance. These capabilities open possibilities for devices that seemed purely fictional just decades ago. Quantum dots represent a bridge between atomic and bulk material properties. These nanoscale semiconductor particles can be tuned to emit very specific colors by controlling their size with atomic precision. The quantum confinement of electrons and holes within these tiny structures creates discrete energy levels similar to those in individual atoms. Applications of quantum dots range from high-definition displays with unprecedented color purity to biological markers that can track individual molecules within living cells. Their size-tunable emission makes them ideal for creating displays with wider color gamuts and better efficiency than conventional technologies. Medical applications exploit their brightness and stability for long-term imaging studies. The synthesis and application of quantum dots continues to expand as researchers develop new materials and fabrication techniques. Different semiconductor compositions offer emission across the entire visible spectrum and into infrared wavelengths. These engineered light emitters demonstrate how quantum mechanics can be harnessed for practical technologies. Supercontinuum generation creates extremely broadband light from narrow-band laser sources. When intense laser pulses travel through specially designed optical fibers or crystals, nonlinear optical effects spread the light across a vast range of wavelengths. This process can transform a single color laser into a source spanning the entire visible spectrum and beyond. The mechanisms behind supercontinuum generation involve complex interactions between light pulses and the materials they traverse. Self-phase modulation, stimulated Raman scattering, and four-wave mixing all contribute to the spectral broadening. Understanding and controlling these processes enables the creation of white light laser sources with unique properties. Applications of supercontinuum sources include advanced microscopy, spectroscopy, and optical coherence tomography. The broad spectrum and coherent nature of these sources provide capabilities not available with conventional light sources. Medical imaging benefits from the deep penetration and high resolution possible with supercontinuum illumination. Terahertz radiation occupies the gap between infrared light and radio waves, offering unique capabilities for imaging and sensing. This region of the electromagnetic spectrum can penetrate many materials that are opaque to visible light, while providing information about molecular structure and dynamics. Terahertz waves can see through clothing and packaging while remaining safe for biological tissues. Generating and detecting terahertz radiation requires sophisticated techniques that bridge optical and electronic technologies. Ultrafast laser pulses can create terahertz bursts through various nonlinear processes, while specialized detectors can measure these weak signals with high sensitivity. The development of practical terahertz sources and detectors enables new applications in security, medicine, and material science. The unique properties of terahertz radiation make it valuable for quality control in manufacturing, detection of concealed objects, and characterization of pharmaceutical products. This portion of the electromagnetic spectrum reveals information about materials and structures that remains hidden at other wavelengths. Optical clocks use the oscillations of light to measure time with unprecedented accuracy. These instruments compare laser frequencies to atomic transitions, creating timekeepers so precise they would gain or lose less than a second over the age of the universe. The stability of optical frequencies makes them ideal references for the most demanding timing applications. The development of optical clocks pushes the boundaries of measurement science and fundamental physics. These instruments are sensitive enough to detect gravitational time dilation over height differences of centimeters, opening new possibilities for testing relativity and searching for variations in fundamental constants. They might even enable new types of gravitational wave detectors based on timing measurements. Applications of optical clocks extend beyond basic science to practical systems requiring extreme timing accuracy. Global positioning systems, high-speed communication networks, and financial trading platforms all benefit from more precise time standards. The ability to measure time with optical precision continues to drive technological advancement. Plasmonics exploits the interaction between light and electrons in metals to manipulate electromagnetic fields at scales much smaller than the wavelength of light. Surface plasmons, collective oscillations of electrons at metal surfaces, can concentrate light into nanoscale regions, with intensities far exceeding the incident illumination. This field enhancement enables new approaches to sensing, imaging, and light harvesting. Plasmonic structures can act as antennas for light, capturing electromagnetic energy and concentrating it into tiny volumes. These optical antennas enable single-molecule detection, enhanced photochemistry, and improved efficiency in solar cells. The ability to focus light well beyond the diffraction limit opens possibilities for nanoscale photonics and optical processing. The combination of plasmonics with other nanoscale phenomena creates hybrid systems with unprecedented capabilities. Plasmonic enhancement of quantum dot emission enables brighter and more efficient light sources, while plasmonic sensors can detect individual molecules through their effect on localized electromagnetic fields. Light-based manufacturing techniques use photons to create, modify, and assemble materials with precise control. Laser processing can cut, weld, and shape materials with accuracies measured in micrometers, while photolithography enables the mass production of electronic circuits with features smaller than the wavelength of light used to create them. These optical manufacturing methods drive modern technology from computer processors to medical devices. 2-photon polymerization allows 3-dimensional printing at resolutions approaching the molecular scale. By focusing ultra-fast laser pulses into photosensitive materials, manufacturers can create complex 3-dimensional structures with features smaller than the wavelength of light. This technique enables the fabrication of photonic crystals, microfluidic devices, and biological scaffolds with unprecedented precision. Optical manipulation during manufacturing extends to the assembly of components too small to handle mechanically. Laser tweezers can position individual nanoparticles, while optical forces can align and orient materials during fabrication. These light-based assembly techniques enable the creation of structures that would be impossible to build through conventional mechanical methods. The future of light-based technology promises even more remarkable capabilities. Researchers work toward perfect light absorbers that could revolutionize solar energy conversion, optical computers that process information at light speed, and quantum communication networks secured by the fundamental laws of physics. Each advance in our understanding of light opens new possibilities for harnessing its properties. As we continue to explore light's mysteries, we discover that this fundamental aspect of nature holds keys to technologies we can barely imagine. From the quantum realm to cosmic scales, light continues to illuminate both our understanding of the universe and our ability to shape the world around us. The journey through light's domain reveals that we have only begun to unlock its full potential. The speed of light remains not just a number, but a gateway to understanding the deepest principles governing reality. In its constant journey through space and time, light carries information, energy, and possibilities that continue to transform our world in ways both subtle and profound. As you drift toward rest, perhaps you can imagine yourself traveling alongside these photons, moving at the ultimate speed through the vast cosmos, witnessing the universe unfold at the pace of light itself. Light sculpts the very fabric of space and time in ways that challenge our deepest intuitions about reality. When massive objects accelerate through space, they create ripples in space-time itself, gravitational waves that propagate outward at exactly the speed of light. These cosmic tremors carry information about the most violent events in the universe, from colliding black holes to the collapse of massive stars into neutron stars. The detection of gravitational waves opened an entirely new window on the cosmos, one that operates independently of electromagnetic radiation, yet moves at the same fundamental speed. When the first gravitational wave signal was detected in 2015, it arrived at Earth after traveling over 1 billion years through space, maintaining perfect synchronization with the speed limit that governs all massless phenomena. This connection between gravitational waves and light speed reveals something profound about the structure of spacetime itself. Both phenomena propagate at the maximum possible speed because they travel through the geometric fabric of the universe rather than requiring any material medium. Space and time provide their own highway, and this cosmic speed limit represents the maximum rate at which any influence can spread through that highway. The relationship becomes even more intriguing when we consider that both light and gravitational waves can be stretched by the expansion of the universe itself. As these signals travel across cosmic distances, the expansion of space elongates their wavelengths, creating redshift effects that allow astronomers to measure both distance and the rate of cosmic expansion. The universe uses its own growth to encode information into the very signals that traverse it. Light interacts with exotic states of matter in ways that reveal the quantum nature of empty space itself. In the most powerful particle accelerators, scientists create conditions so extreme that the vacuum begins to behave like a material medium. Virtual particles pop into existence from pure energy, borrowing against the uncertainty principle before disappearing back into nothingness. These vacuum fluctuations can actually affect the propagation of light in measurable ways. In the presence of extremely strong electric or magnetic fields, the quantum vacuum develops optical properties similar to those of ordinary materials. Light can scatter off these virtual particles, change its polarization, or even split into multiple beams. The empty space between stars and galaxies, far from being truly empty, teems with quantum activity that subtly influences every photon passing through it. This quantum foam, as physicists sometimes call it, represents the smallest possible scale of space and time. At the Planck length, approximately 10 to the negative 35th meters, the smooth geometry of spacetime breaks down into a frothy sea of quantum fluctuations. Even light, traveling at its constant speed, must navigate through this fundamental graininess of reality, though the effects remain far too small to observe directly with current technology. The polarization of light carries hidden information about the magnetic fields it encounters during its journey through space. As light travels from distant stars and galaxies, it interacts with charged particles and magnetic fields throughout the cosmos. These interactions can rotate the plane of polarization in predictable ways, creating a kind of magnetic map of the universe written in the orientation of light waves. Radio astronomers use this polarization information to study magnetic fields in our galaxy and beyond, revealing structures invisible to conventional imaging. The magnetic field lines that thread through interstellar space become visible through their effects on polarized light, showing how cosmic magnetic fields channel the flow of charged particles and influence the formation of stars and planets. Even the cosmic microwave background radiation carries polarization signatures that encode information about the early universe. The patterns of polarization in this ancient light reveal details about the conditions that existed when the cosmos first became transparent to electromagnetic radiation. These subtle signatures might even carry evidence of gravitational waves from cosmic inflation, the rapid expansion thought to have occurred in the universe's first moments. Light exhibits memory effects when it passes through regions of curved spacetime. As electromagnetic waves traverse the gravitational fields of massive objects, they carry information about that journey encoded in subtle changes to their waveform. This gravitational memory persists even after the waves have moved far from the source of curvature, creating permanent alterations in the light's characteristics. These memory effects provide astronomers with tools for studying massive objects that might otherwise remain invisible. The slight changes in timing, frequency, and polarization that result from gravitational interactions can reveal the presence of dark matter concentrations, primordial black holes, and other exotic objects that don't emit light themselves, but leave their fingerprints on passing electromagnetic radiation. The phenomenon extends beyond individual photons to affect the entire geometry of light propagation through the universe. Gravitational lensing creates multiple images of distant objects, delays the arrival of light from different paths, and magnifies the apparent brightness of background sources. These effects turn massive galaxy clusters into natural telescopes that allow us to peer deeper into space and further back in time than would otherwise be possible. Coherent light exhibits phenomena that seem to violate our intuitions about the discrete nature of photons. When laser light interacts with specially prepared materials, it can create conditions where individual photons become correlated across macroscopic distances. These quantum correlations persist even in bright laser beams containing trillions of photons, suggesting that quantum effects can scale up to sizes visible to the naked eye. Researchers have created states of light where quantum uncertainty is squeezed below the standard quantum limit, redistributing the natural fluctuations in ways that enhance measurement precision. These squeezed states of light enable gravitational wave detectors to achieve sensitivities that would be impossible with classical light sources, pushing the boundaries of what can be measured in the universe. The study of quantum light also reveals connections between information theory and fundamental physics. The amount of information that can be encoded in electromagnetic radiation depends not only on classical properties like intensity and frequency, but also on quantum characteristics such as entanglement and squeezing. These quantum information channels might enable communication and computation capabilities that transcend classical limitations. Atmospheric optics create some of nature's most spectacular light displays through the interaction between solar radiation and water vapor, ice crystals, and dust particles in the air. Halos, sundogs, and light pillars result from the refraction and reflection of sunlight by ice crystals with specific orientations and shapes. Each type of atmospheric optical phenomenon requires precise conditions that occur only under particular combinations of weather and lighting. The complexity of these displays reveals the sophisticated ways that light interacts with matter on multiple scales simultaneously. Individual ice crystals act as tiny prisms and mirrors, while collectively they create patterns that span the entire sky. The same principles that govern laboratory optics operate in the atmosphere, but on scales and with complexities that dwarf human engineering capabilities. These atmospheric effects also influence how we observe astronomical objects. The twinkling of stars results from turbulence in Earth's atmosphere that constantly changes the path of starlight. Atmospheric dispersion separates different colors of starlight, creating brief flashes of color as stars rise and set. Understanding these effects allows astronomers to correct for atmospheric distortions and recover the true properties of celestial objects. Light therapy represents one of the most direct applications of our understanding of photon interactions with biological systems. Different wavelengths penetrate tissues to various depths and interact with specific cellular components in ways that can promote healing, reduce inflammation, or trigger beneficial biochemical reactions. Red and near-infrared light stimulate cellular energy production, while blue light can eliminate certain bacteria and regulate circadian rhythms. The mechanisms behind phototherapy involve the absorption of specific wavelengths by cellular chromophores, molecules that convert light energy into chemical signals. These photochemical reactions can activate healing pathways, increase blood flow, and stimulate the production of beneficial compounds within cells. The precision with which different wavelengths target specific biological processes demonstrates the intimate connection between light and life. Research continues to reveal new applications for therapeutic light, from treating seasonal depression with bright light therapy to using precisely tuned lasers for targeted cancer treatments. The ability to deliver energy directly to biological systems through controlled light exposure offers possibilities for non-invasive medical treatments that work with the body's natural healing mechanisms. Ultra-fast laser pulses create conditions where light intensity becomes so extreme that ordinary matter behaves in extraordinary ways. When laser pulses shorter than a trillionth of a second are focused to tiny spots, they can strip electrons from atoms faster than the atomic nuclei have time to respond. This creates exotic states of matter where electrons and ions exist in highly non-equilibrium conditions. These extreme light intensities enable the study of physics under conditions that exist nowhere else in the accessible universe, except perhaps in the immediate vicinity of neutron stars or black holes. Electrons accelerated by these intense fields can reach velocities approaching the speed of light, creating relativistic plasma conditions in laboratory settings. The applications of ultra-fast, intense laser pulses extend from basic research into the fundamental properties of matter to practical technologies for medical imaging and industrial processing. Laser-induced breakdown spectroscopy can identify the elemental composition of materials by analyzing the light emitted when intense pulses vaporize tiny samples. These techniques provide rapid, non-destructive analysis capabilities for everything from geological surveys to quality control in manufacturing. The propagation of light through biological tissues reveals the optical properties that make life possible, while also enabling new medical technologies. Living tissues scatter, absorb, and fluoresce light in ways that depend on their structure and biochemical composition. These interactions create the characteristic appearance of healthy and diseased tissues, forming the basis for optical diagnostic techniques. Near-infrared light can penetrate several centimeters into biological tissues, allowing non-invasive monitoring of blood oxygenation, glucose levels, and other physiological parameters. The development of biocompatible optical fibers enables light delivery and collection deep within the body for both diagnostic and therapeutic applications. These optical approaches complement traditional medical imaging by providing real-time information about tissue function rather than just structure. Biophotonics, the study of light interactions with biological systems, continues to reveal new phenomena and applications. Some organisms produce light through chemical reactions with efficiencies approaching 100%, far exceeding artificial light sources. Understanding these biological light generation mechanisms could inspire new approaches to efficient artificial lighting and display technologies. The speed of light creates fundamental limits on parallel processing in optical computers. While light travels incredibly fast, it still requires finite time to cross even microscopic distances within optical processing systems. This limitation becomes significant when designing optical computers that must synchronize operations across multiple processing elements, operating at light-speed frequencies. The challenge lies in maintaining coherence and timing relationships between optical signals as they propagate through complex processing networks. Small variations in path length can cause signals to arrive out of phase, leading to processing errors. Optical computer architects must carefully design systems that account for these propagation delays while maximizing the parallel processing advantages that light offers. Despite these challenges, optical computing promises revolutionary capabilities for specific types of calculations. Pattern recognition, image processing, and certain mathematical operations can be performed optically with speeds and efficiencies impossible to achieve with electronic systems. The key lies in matching the computational task to the natural strengths of optical information processing. Nonlinear optical effects become increasingly important as laser powers continue to increase, and new materials with enhanced nonlinear properties are developed. When light intensities reach threshold levels, materials begin to respond in ways that depend on the square, cube, or higher powers of the incident intensity. These nonlinear responses enable frequency conversion, optical switching, and signal amplification. The development of materials with tailored nonlinear properties allows engineers to design optical systems with unprecedented capabilities. Crystals with engineered domain structures can efficiently convert infrared laser light into visible wavelengths, while specially designed glasses exhibit non-linear responses at much lower power levels than conventional materials. These advances in nonlinear optics enable new types of optical devices that can perform complex signal processing functions entirely in the optical domain. All optical switches, optical amplifiers, and wavelength converters form the building blocks of advanced optical communication systems that could eventually replace electronic processing in many applications. Light scattering provides information about particles and structures much smaller than the wavelength of the probing radiation. When light encounters objects comparable to or smaller than its wavelength, the scattering process depends sensitively on the size, shape, and composition of the scattering centers. This relationship enables optical techniques for characterizing everything from atmospheric aerosols to biological cells. And so our journey through light's vast domain draws to a gentle close. We've traveled alongside photons across cosmic distances, explored the quantum mysteries that dance at reality's smallest scales, and witnessed how this fundamental force shapes everything from the birth of stars to the thoughts flowing through your mind right now. Each insight has revealed light not merely as illumination, but as the universe's most eloquent storyteller, carrying messages across space and time at the only speed that truly matters. Tonight, you've glimpsed the elegant physics that governs existence itself, from the 8-minute journey of sunlight to the quantum entanglements that connect particles across impossible distances. Perhaps some of these cosmic truths will linger as you drift towards sleep, or maybe they've already dissolved into the soft rhythm of rest. Either way, the mysteries remain, patient and eternal, waiting in the gentle glow that surrounds us always. The speed of light stands as more than a cosmic speed limit. It's the thread that weaves space and time together, the constant that defines causality itself, and the messenger that brings us news from the furthest reaches of existence. As your eyes grow heavy and your thoughts begin to slow, remember that you are always traveling through this universe at light's own pace through time, carried forward by the same fundamental forces that guide photons across the cosmic dark. Sweet dreams, fellow traveler, and may your rest be as peaceful as light's eternal journey through the infinite night.